Hi again. Okay, we're moving on to our second video in the chapter on electronic structure and periodic properties. And we're going to talk now about line spectra. We've learned before about wavelengths of light and the frequency of light and the energy of light and how we can think of light as a particle and as a wave, and how some problems that folks ran into led to new understandings about light. So the Planck explained the ultraviolet catastrophe by invoking the idea that light could be made of particles, and Einstein used that to explain the photoelectric effect. So at this point we're thinking of light both as a wave and a particle, and we're going to run into a problem that led us to pretty close to where we are in our modern understanding of how electrons are connected up to atoms, how they relate. So the issue is called line spectra. Line spectra, and I'll just mention spectra is the plural. Spectrum is the singular. So if it's one of them, you say you're looking at a spectrum. If it's more than one, you say you're looking at spectra. It's one of those weird Latin words where the plural ends in A like that. All right, so we're going to see in just a minute, and really it's much easier to look at a picture, I think. So let's go on down here and look at figure 313. So what we've got here is we have got a picture of some spectra. And the numbers you see on there, the 4,000 A, 5,000, 6,000 down here, this is the wavelength, and that's in angstroms. And if I remember right, 1 angstrom is, I want to say that's 10 to the negative 10 meters. I think that's the right conversion factor for that. An angstrom, spell it A-N-G, angstrom, is an old unit that was used to talk about very small distances. An angstrom is a useful unit because bonds are about in the order of like 1 to 5 angstroms normally. All right, so at the top here, what we have is a continuous spectrum. Continuous spectrum, and of course this 4,000 angstroms is 400 nanometers. And you can see this is down on the violet end of the spectrum, and then over here we go to the red spectrum, down around 700 nanometers. So longer wavelength, shorter frequency and all. Now, these other spectra here are called line spectra. And as you see, they're dark except for a few individual lines. And if I blow it up even more, you can see, looking at that hydrogen spectrum there, you see maybe 4 lines in hydrogen that are at a single wavelength value. There might be a couple of closely stacked lines, but I think it's 4 at a single level. You look at sodium and calcium and mercury there, they have other distinct patterns, and it may immediately spring to your mind that these spectra might be a way to identify these different atoms, and that's absolutely correct. These are used. There's atomic absorption and atomic emission spectroscopy is a common tool that's used to identify elements. But where did those lines come from, right? So go back here to the previous slide. Okay, each line is a single wavelength of light, and that means that's what we call a discrete energy, which is to say it's a single value of energy, and thus that means that the energy is quantized. Now, why on earth would there be only certain energies emitted? And the way you generally do these things is you'll take your sample. So you take a tube with a little bit of hydrogen gas in it, almost a vacuum, and you pass an electrical current through it, and the electricity will cause the electrons to become excited, and they will undergo transitions and then relax back to the normal setup of electrons, as we'll learn. And when they relax back, they give off these lines, these characteristic lines. So that line right there, that I'll just try to trace with the mouse here. So you see this line right here, for example, is due to a very specific transition of electrons in the hydrogen ion. This one is due to a different, very specific transition. So, make this bigger. The guy who gets credit for explaining this was a guy by the name of Niels Bohr. He was Danish. Niels Bohr put together the observations of a lot of other people and then was able to basically generalize it in such a way that it was kind of his own creation. And the idea was that that there were only certain allowed orbits that the electrons could be in. And so let's see if we have a picture here of this. Oh, I don't think we have a good picture of this. So let me pull something out here, and I'm gonna get us an image. So what I'm gonna do is I'm gonna go to my folders here, and you can't see this because I'm off screen, but I'm gonna go and pull a file up here that that I think is especially helpful. All right, so what you're seeing here, this is the chemistry reference tables for the state of North Carolina that they use for their general chemistry courses, and this is what students have available on every exam, and I think it's a pretty good handout. And down here at the end, we've got this this Bohr model picture that I think is quite good, and I'm going to make that small enough that we can see what we need to see here, like so. And I'm going to use my snipping tool here, which is something that you have in Windows, and I'm going to snip a copy of this, and I'm going to copy that, and then I'm going to go back to our notebook, and I'm going to see if I can fit this in, paste this in here somewhere. If I can get a paste option. And so that kind of set it on top of things. I don't want to do that. Let me see if I can make that a little smaller so we can see it. And drop it down here somewhere where it makes more sense. Pick it up and slide it down here. All right, bear with me there. I think it'll probably make better sense to put it over here on the side and reduce it down smaller. All right, so these are these orbits for the hydrogen atom. So you've got here these basically different orbits, and they start at number 1 here and go up to 2, 3, 4, 5, and 6, and they go further than that, but that's what they mean. So when they talk up here about this idea of quantization being provided in this, that means that we've got this picture of these orbits. Okay, and the nice thing about this North Carolina handout is it gives you actually, these are wavelengths, so these are in nanometers. It's wavelength of specific transitions going from one level to another. So like this level right here, so this is level 1, 2, this is level 3, this is level 4. So this is the transition going from 4 to 3 that gets us a line at 1875 nanometers, and you see that's in the infrared. For that one, so you can look at some of those values there. Now, going back up here to the textbook slide, basically what Bohr said was that the energy of the photon that was emitted would be equal to hc over lambda, where lambda is the frequency of it, and that would be given by the difference of the energy between the final, F is for final, and I is initial. So the difference in the two energies, the lines here refer to absolute value. And that just means that whether the number is positive or negative, you make it into a positive number. So if I were going from 2 to 4, that would be, the difference would be, I think, negative, and that would represent light being absorbed, and then we'd report it as a positive number. The wavelength can't be negative. And then if I went from 4 to 2, it'd be the same value, but it'd be a positive number, and that would be light being given off, or energy being given off, so in the form of light. So this is the formula for calculating the energy for each level. So to get any level here, we can get it with this formula. We have to know what the level is and what the value of K is. And those n's are our first quantum numbers that we see. If you put this formula together, you can get a what's called a Rydberg equation, and you have to know the values. It's kind of a complicated sort of equation, but this kind of thing can give you the wavelength for any transition, and the value of that constant is known. Now, this is another way of looking at the orbits. So again, if I'm talking about my picture of orbits here, where that's 1 and that's 2 and that's 3 and so on, that 3 here is relating to that level right there. The 2 here is relating to that level right there, and that 1 is that level right there. These are negative numbers relative to 0, right? So basically what it's saying to 0 would be, losing the electron completely. And so it would take 2.18 times 10 to the negative 18 joules to knock one electron completely off of a hydrogen atom. And we can look at the differences between those and figure out what the energy difference is, and thus what the frequency and the wavelength of the light would be. So the idea is that these electrons are normally going to be in the most stable configuration, which is the lowest possible energy, and that's known as the ground state. If we knock them up to an excited state, they have a higher energy. So if I look at my hydrogen atom here, so that's my nucleus, and here's my electron in level 1. Okay, so this is level 1, level 2, level 3. I can put some electrical energy in here. I'll write it like that. That might knock that electron up to level 3, right? So this is the ground state. This is an excited state. And then what can happen is this can go back to the ground state, and when it does, it's going to give off light. And the energy of that light is going to be equal to h nu, or hc over lambda. And that energy is going to be equal to the difference between, that energy is going to be equal to the delta E from 3 to 1. So the energy for level 3 minus the energy for level 1, absolute value, is kind of how you tie that all back into. So the electron here got knocked up to this level by the electricity, and then to come back, it falls back down to that level and gives off that light, which we'll say right as h nu. And that's basically what this slide says. And so what's really weird about this, and I think the thing that's hard to appreciate, is Bohr saying that the electron can only have certain energies, and that's like saying that you could drive a car at 15 miles an hour, or you could drive it at 25 miles an hour, but you couldn't drive it at any energy level between 15 and 25. Okay, now that doesn't make sense to us here in the macro world we live in. We're the big world, but when you get down to the level of an electron, weird things like that become true. Now, the other way of thinking about this is like a set of stairs, or like a ladder, right? So here's a ladder, and if I am going up this ladder, my transitions of my foot had better be from 1 to 2 to 3 to 4, etc. If I go to 2.5, that's not going to work out very well, and I might wind up falling off the ladder and breaking my neck. Or if I'm climbing stairs, I can't go to the 2.5 stair level. So there are things in our experience that are kind of like this. Here's another diagram, again, where we're showing the different energy levels over here for the hydrogen atom. So these are our different orbit levels or energy levels, and you've got the over here you've got the excitations, where the energy is being put in and the electrons are getting knocked up to a higher orbit. And then on the right-hand side of this, you then have where it's relaxing back to the ground state or back to a more stable state. And every one of those transitions is going to give you a different line in the line spectrum, but it's going to give you a line. Now, the problem with the Bohr model. The Bohr model works great for hydrogen. It works great for anything that only has one electron. You have to take into account that there's more protons on the atom. So I do uranium, which has got 92 electrons. If I talk about the uranium 91 plus atom, it's only got one electron. I can explain its behavior using the Bohr model. Now, is that very practical? No, you'll never find any real uranium 91 plus atoms out there unless you're in a really contrived experiment in a very specialized apparatus. So that was the problem. The Bohr model has got limited utility, but it's very important because it introduced this idea. And it introduced this idea of quantization, the idea that you can only have certain energy values. And so it's almost more important for a historical point of view. So this led to the again to the quantum mechanics thing. So we see here that we got quantized energy levels. We describe them with quantum numbers. The quantum numbers are integers. That means like 1, 2, 3, 4, 5, not 1.1 or so on. And those numbers are important in terms of telling us about the energy. The bigger that number is, the further the electrons away from the nucleus, the higher its energy level it is. And then we're able to explain the spectra based on those quantized energies. So again, a bunch of really important ideas that came out of the Bohr model. So we're going to wrap this one up here. I just want to leave you with one of my favorite stories about Niels Bohr. A lot of this story that we're talking about, a lot of the folks that are involved in this were involved in the development of nuclear weapons during World War II. Niels Bohr was Danish, and of course Denmark was a country that was taken over very early by Nazi Germany. And Niels Bohr fled Denmark, eventually coming to America, where he worked at least a little bit on the Manhattan Project. One of the things he did when he snuck out of Denmark, he was literally escaping in a very small boat. And he carried with him 2 jars, and those jars were filled with what appeared to be a clear liquid. What was in those jars was a solution called aqua regia, which is a mixture of some acids, and it's the only solution that'll dissolve gold. And what was dissolved up in those jars were 2 Nobel Prize gold medals that were awarded to fellow Danes. Now, Bohr had already melted down and donated his own gold medal to the resistance effort, but these Nobel medals were recast from the gold that was in those jars that he smuggled out of Denmark. So Niels Bohr, both a great scientist and a pretty impressive guy. All right, so we'll pick up some more stuff again. I think the slide thing made reference to slide 34, but I think we're good at that point. You've got enough to do that first homework problem, so we're just going to start there, and we'll pick up on slide 32 on the next video.